So the rules for being in scientific notation, in order to be in proper scientific notation, the number must be written with a number between 1 and 10 and multiplied by a power of 10. For example, at the bottom of the screen we have 23 times 10 to the 5th power is not proper notation. Take a guess why. 23 is not between 1 and 10. 23 is not between 1 and 10. We're being multiplied by a power of 10, times 10 to the 5th power. That's totally fine. But the 23 makes this not proper scientific notation because it's not between 1 and 10. So if I take 137 million, I can rewrite this number as 1.37 times 10 to the 8th power. Why the 8th power? We're going to do the 8th power because we're going to take the decimal, which is unseen right here, and we're going to move it to the left until we have a number between 1 and 10. So 1 spot, 2 spot, 3 spots, 4 spots, 5 spots, 6 spots, 7 spots, 8 spots until we get 1.37 and then times 10 to the 8th power because 8 is how many places we had to move the decimal. All right, now this is an opportunity for you to practice, check your understanding. I want you to rewrite these numbers using scientific notation. Please pause the video right now so you can do that. First number in scientific notation will be rewritten as 3.47 times 10 to the 5th power. The second value will be rewritten as 9.02 times 10 to the 8th power. And the third value will be rewritten as 6.14 times 10 to the 4th power. I hope you've noticed that the only digits that we're including in the scientific notation format are significant figures. Notice as you go forward, the only digits you'll include in scientific notation will be those digits that are significant. Here's another check for understanding. So go ahead and press pause and attempt this problem. In the United States, 15 million households use private wells for their water supply. Write this number in scientific notation. Well, we need to find a number that is between 1 and 10. We have 15, so that's not going to work. We can't do 0.15. We can do 1.5, however. That's between 1 and 10. So we'll move the decimal over 1, 2, 3, 4, 5, 6, 7 places, and we'll end up with 1.5 times 10 to the 7th. Here's another check your understanding. Go ahead and pause the video and attempt this problem. The U.S. has a total of 1.2916 times 10 to the 7th acres of land reserved for state parks. Write this in standard form. We are going to take the 12916 and we're going to conserve those because those are all significant figures. And we're going to move that decimal to the right 7 places. 7 places. That'll give us 12,916,000 acres. Let's talk about why negative exponents give us smaller numbers. All right. Here we have 10,000. I want you to note that 10,000 is the same thing as 10 times 10 times 10 times 10. That's 10 multiplied by itself 4 times. 1,000 is 10 times 10 times 10. That's 10 multiplied by itself 3 times. And 100 is 10 times 10, which is 10 multiplied by itself 2 times. 10 is 10 by itself. 1 is 10 to the 0 power. Note, anything to the 0 power is 1. But do you see a pattern here? As we move down from an exponent of 4 to 3 to 2 to 1, notice that these numbers are representing how many zeros we have. All right. So 1 over 10 will be 10 to the negative 1. 1 over 100 will be 10 to the minus 2. 1 over 1,000 will be 10 to the minus 3. And 1 over 10,000 will be 10 to the minus 4. Notice we still have this exponent representing how many zeros or how many times the decimal has moved. This negative sign is indicating that this will now be an inverse. We'll now have 1 over that term. So using this idea, I want you to pause the video and attempt to use scientific notation to rewrite these 3 terms. Please pause the video and do that now. All right, the first value can be rewritten as 8.82 times 10 to the negative 4th. I need to move this decimal to the right 1, 2, 3, 4 places. How do I know I need to move it 4 places? Because I need to get this initial value to be between 1 and 10. That's going to take 4 decimal moves. We're moving to the right so that we're going to make that a negative exponent. Next value, 5.9 times 10 to the negative 7th. All right, we need to move this decimal all the way between the 5 and the 9 so we can create a value between 1 and 10. 5.9 will do just that. How many places do we have to move it? 7. Which direction do we have to move it? To the right. So it's going to be a negative 7. Then lastly, we have 4 times 10 to the negative 5. Again, we have to move the decimal all the way to the right of the 4 to get a number between 1 and 10. How many places do we have to move it? 1, 2, 3, 4, 5 places. Which way do we have to move it? To the right. So that's a negative 5 for an exponent. Moving on, I want you to be able to distinguish between inversely and directly proportional relationships. Okay? Graphs show relationships, so we'll be using graphs to represent this in shorthand. So there are a couple different kinds of relationships you can show with a graph. There's the linear relationship, which is direct proportionality, and you're going to see a linear graph. Well, there's also nonlinear graphs, which are also known as indirect proportionality. But there's a few different types of these. We have things like inverse, we have exponential or quadratic proportionalities, or we also have oscillating proportionalities. But what we are going to focus on in this class is the direct proportionality, which is going to be a line, and the inverse proportionality, which will end up being have a negative hyperbole. So we have the negative relationship, which is direct proportionality. Okay, that's a straight line which passes through the origin. Okay, so 0, 0. You can have a straight line, and it won't actually show a positive, a direct proportionality unless it goes through the origin. So it has to go through the origin. That's part of the definition. But we have that as a straight line. And we can see that the equation y equals kx is responsible as what defines a direct proportionality. But what I want to point out to you is as x gets bigger, so does y. As x goes up 1, y goes up 1. As x goes up 2, y goes up 2. As x goes up 3, y goes up 3. And so whatever change happens to x, the exact same change happens to y. That's a direct relationship. Whatever happens to one happens to the other. And we can contrast that with our other relationship, inverse. Okay, instead of having our equation be y equals k times x, here we have y equals k divided by x. And what this means is one variable increases, the other variable will decrease. Okay, k here is referred to as a constant. K is whatever number fixes the equation and makes it true for both x and y. And what graph we're looking for here is something like this. Okay, notice that starting here at x equals 1, we have y equals 10. As we change x so that x equals 2, we've gone up 1, y goes down. As we continue to increase x, y continues to drop. The further we increase x, the further y will have decreased. We're going to get this exponential curve moving down. Okay, moving down. This is an exponential curve moving down. Now, how is this direct proportionality and inverse proportionality work with us in chemistry? One main example is density. If you remember density, we have density is equal to mass divided by volume. Okay? Density is going to have a direct relationship with mass and an inverse relationship with volume. Okay? Density is going to have a direct relationship with mass. That means as mass goes up, density will also go up. Okay? But conversely, as volume goes up, density will go down. Density will go down. So that means an inverse relationship. All right, let's have a few learning checks in here. First question I'll throw at you. Which type of proportionality is shown by the following graph? Correct answer is B. With the inverse proportionality, the hyperbole results when one variable depends on the inverse of the other. If you go back to the equation that describes that inverse proportionality, you're going to see that it's y equals k divided by x. Right? So y is equal to the inverse of x. So that's an inverse proportionality. Moving on, learning check 2. Which proportionality can be written as y equals k times x? The answer is A. Okay. Reason being, your misspelling. Direct proportionality is written as y equals k times x plus b. That is a equation for a straight line, where b is a y-intercept. If the y-intercept is 0, the above equation can be rewritten as y equals kx, which is the equation that you see in your book, and that's the version of the equation that you're going to see on the quiz and on your test. I know this has been a long video lecture, but there was a lot to go over. Hopefully you took the time to practice the various problems that I provided for you, and we will work on this more in class. I will see you next period.